Peace be upon you and God's mercy and blessings. And upon you be peace and blessings. All right, we talked about magnetic resonance imaging. Last time we had a simple introduction. Right, we will go over some other points with a few more details so that you all can stay focused. If there's anything you missed from last time, we will focus on it again, God willing. We talked last time about magnetic resonance imaging, and the idea in the imaging process relies on searching for the system or looking for differences between different tissues in a certain property. The CT and X-ray focus on the physical properties or the densities of materials or their atomic numbers and the differences in the attenuation coefficient. Bone absorbs a lot while air does not, and soft tissue in between gives me a difference in attenuation, providing an image based on this difference in the magnetic field. We work on the tissue characteristics or the magnetic characteristics of different tissues. Not all tissues respond the same way. If I apply an excitation radio frequency pulse or a magnetic field, or if I magnetize them, they start to receive the signal or lose the magnetization at the same speed or in the same manner. This creates a difference between the tissues in their magnetic properties. So when they were looking for atoms with more sensitive magnetic properties, hydrogen atoms were the ones. Why hydrogen atoms? Because in their nucleus they have a proton, and this proton is considered an odd number. One proton, an odd number of protons. This gives it a certain quality that makes it more sensitive compared to other tissues or materials. So I will work with hydrogen. Now, what is inside hydrogen? Inside it, there is a nucleus, and within that nucleus, there is a proton. My work focuses on the proton that exists within the hydrogen atom. Of course, it is found in water and in many materials, or it is present in fats and in most structures or chemical compounds that exist in our bodies. They contain hydrogen atoms. So now I will work on the proton that is inside the hydrogen atom. My proton is hydrogen. My proton. The whole idea is that I have a proton in the tissue and I give it a signal. Then I stop it and the tissue starts to respond. I receive this signal and translate it into images, the same images that we see here. I will clarify these processes. 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 As I previously mentioned, I depend heavily on hydrogen atoms. This is because the sensitivity of hydrogen atoms is considered significantly higher when compared to other materials such as fluorine, sodium, and phosphorus, including, as you can clearly see. This is because it has a relatively old mass number. Inside each hydrogen atom, there is a single proton, which inherently has a charge. This charge moves in a spinning motion, rotating continuously around itself, similar to how the Earth rotates around its own axis. Despite having no external charge, it still generates an intrinsic magnetic field, thus becoming a small magnet. Specifically, in the case of the proton, which possesses a positive charge and spins around its own axis, it effectively acts like a magnet. As we previously mentioned, our human bodies contain countless billions of protons, therefore we essentially have numerous magnets within us. However, does this imply that we are capable of attracting the metals around us? The answer is no. As we have stated, it equals zero because the protons in our bodies are in a state of complete chaos, indicating that each proton is in its own specific state. In a proton, if this keeps apart or makes our resultant zero, then if I bring what is in, the magnetic force results in B. So if I bring in the protons, when protons are placed in a magnetic field, they become aligned with the main magnetic field, which has two poles, the south pole and the north pole. This alignment occurs for the protons, which align with the magnetic field direction. The number of protons aligned with the magnetic field will be greater than those that are antiparallel. If we say there are 1 million protons aligned upwards in a relaxation state and 1 million downwards, we can say that the 1 million will cancel out the other million, leaving us with some protons aligned with the main magnetic field, which I refer to as the B node. I will work with these protons to obtain my image and excite them. When these protons are placed in a magnetic field, they gain alignment with the magnetic field lines and acquire a motion called precision motion. As we can see, the protons start to rotate around the main magnetic field axis. Your speed depends on the strength of the magnetic field. Specifically speaking, indeed, the strength of the main magnetic field from the machine, whether we are talking about 1 Tesla, 2 Tesla, 3 Tesla, or 0.5 Tesla, which is the B node. The higher this B node increases, the faster your rotational speed will be, depending on what you say equals the type of material you are discussing. You multiply this by the B node, and then you can determine the angular frequency or precession frequency, which is essentially the rotational speed. So why do we use rotational speed, or why is it important to know the precession frequency? It is so that we can achieve resonance, which means you provide a pulse or give energy to these protons that are moving at a certain speed. And since you know their speed, energy exchange will start to occur, allowing you to give them energy, because if it is moving at a certain speed and I give it energy at a different speed, energy transfer will not occur. Therefore, the frequency with which I am sending the pulses must be the same as the frequency of the protons that are present. I illustrated this by saying that if you have two cars in a race and both are moving at the same speed, our energy transfer becomes very easy. However, if one of them is moving at a different speed, the energy, or our sandwich, or the energy will experience loss. This is what happens to you in the radio machine as you are tuning to adjust the frequency to achieve resonance between the frequency present in the environment around you and the frequency of the radio antenna you have, so that this resonance occurs and you can receive your wave. That's why I called it magnetic resonance imaging, because it relies on the magnetic field and resonance. This resonance occurs between the external radio frequency pulse and the precision motion of the protons present in the body of the patient. So after that, the protons present in the magnetic field have acquired, as I mentioned, two things. The first is that they became aligned with the direction of the main magnetic field, or in an antiparallel configuration. The number of protons in the antiparallel state is always less than that in the parallel state. The protons that I refer to as being above are in a relaxation state, while those below are in an excitation state. Like someone who makes an effort to stand on their hands, I call one of them the difference, which is the number 7 that I mentioned, which is between 1,000,000 and 7, looking above 1,000,000 and 7, looking below. Okay? Now I have the protons looking up, which added to the main magnetic field. So I have a net positive with the protons looking up with me. Now I said that I need to change the direction of their magnetic field, which is coming from the protons, to be opposite. Why do I need to reverse its direction? So that I can measure it, because if the magnetic field is in the same direction as the main induced magnetic field, I won't be able to tell if it's coming from the protons or from the main magnetic field. It's like someone filling water from a hose into a river. The river is the main magnetic field, and the hose is the protons that have their own magnetic field. So I'm adding their magnetic field to the main magnetic field. You cannot measure the amount of magnetic field coming from the protons at that time. You can't measure it. But if you change the direction of the magnetic field coming from the protons and make it in another direction outside or perpendicular to the main magnetic field, then you can measure it. In this case, you can measure it, which is why I create excitation or change its orientation by altering the direction of the protons to generate a magnetic field in another direction. This magnetic field in another direction allows me to take measurements and see how high its peak is. Of course, for the resonance frequency or the angular frequency of different materials, you will find 42.5 million hertz for hydrogen if you place the protons in 1 Tesla. Increasing the Tesla will increase your frequency. The more you increase the magnetic field force, which is the B node, the more your angular frequency or resonance frequency will increase. I said that I have a set of RF pulses and I know the frequency, so let's apply the RF pulses through your coil and perform excitation. After that, stop the RF pulses, perform relaxation, and receive the signal. It is not easy like that. It's not as simple as you might think, as you will encounter some issues. What are these issues? If I have an organ shaped like this is the organ you envision, and you want to take a slice here, or a slice here, or a slice here. Each of these slices, if I give you an RF pulse, will be excited all at once. Therefore, when the RF pulse stops, they will all be excited, and you will start receiving the signal. You cannot differentiate this signal from any slice at that moment. You need to do something. What should I do? You must first perform excitation for one of these slices. All right, so what we did is something called slice selection gradient. You have it here. This is the basic magnetic resonance device. The magnetic resonance device consists of a bore shaped like this. This is the bore, where the patient lies or enters into the main magnetic field. The main magnetic field is the primary magnetic field, which has 2 poles, north and south. This is the main magnetic field. There is something called the shim coil, which measures the homogeneity of the magnetic field. This magnetic field must be homogeneous, meaning that when I say I have a machine with 1 Tesla, it means that the magnetic field at any point within my field, where I am imaging, should not have any variation. The shim coil measures this magnetic field and tells me that there is homogeneity in this magnetic field. The shim coil is embedded. It is a fixed component in my machine. The gradient coil comes after this. The gradient coil is what I use, and I have 3 gradient coils. One is called the slice selection gradient coil, and the second topic is the phase encoding gradient coil, and the third is the frequency encoding gradient coil. I can change these 3 based on the type of slice I am imaging. Do I want a slice or not? What are these 3 used for? As we discussed yesterday, we said that you use these 3 for something called taking your image. Okay, what is it? In simple terms, first I have 3 present. What are the 3? The Y, and X and Z. The Z is the one that corresponds with the patient. The Y is perpendicular to the patient. The X means you are moving from left to right. The Y-axis is vertical from top to bottom. The Z-axis moves as if you are moving through the patient's body until you reach the head in relation to it. In the third direction, I can adjust my gradients, which change the main magnetic field. The term gradient means to vary the magnetic field strength in the Z, Y, or X directions as desired. So, in the Z, Y, or X directions, we have 3 gradients, one in Z, another in Y, and the third in X. I determine their positions based on the type of slice or sequence I will take, whether it is axial, coronal, or sagittal. The three gradients can be slice selection in Z, Y, and phase encoding in X, or vice versa, depending on the type of slice. Now let's see how I use these gradients. First, I use them for something called special encoding, as you will see this term frequently. You take the signal coming from subatomic particles called protons, record it, and in the end, you get your image, ultimately resulting in your final image. This signal or signals you receive from a patient come at a specific time interval with particular frequency characteristics and amplitude levels. When I say this signal is a sine wave type of signal, for example, this very same kind of signal has its own unique frequency value associated with it. What does frequency mean? It means measuring how often peaks reach their topmost point as well as their lowest bottom. Okay. For me, cycles essentially symbolize a cycle of each type, and frequency represents the number of these cycles per second. So that's in essence what we call frequency. As for amplitude, it refers to the distance or height of its peak point. Fundamentally speaking, it can be a low amplitude or high one, where both can have identical frequencies. Thus, this represents excess in terms of amplitudes, now time. When I say I have a signal like this is the time. If there is another signal, this signal starts here. For example, at this point and ends at this point. Now, if I have another signal, this signal might look like this. So, if these two signals are in different time frames, when I receive a signal at one time, and then another signal comes in at a different time, you will find that this signal starts here. This signal started first, and then this signal follows. So, you have the different time signals of this signal, and I call this the idea of out of phase. What does out of phase mean? It means that the signal you receive might come at the same frequency, but differ in timing. This is the game. The idea of encoding is that you want to differentiate between the signal coming from the patient, either in different frequencies or coming at different times, and you can distinguish between them. This is what we do with our three gradients. You make each pixel in the image contain a set of protons that can play in frequency and phase. Phase means you make them out of phase, and their frequency changes. In this case, you will receive a signal that comes at a different time. When it comes at a different time, you will see its value, which expresses its magnitude. If its value is high, you will place it accordingly. If it is low, you will place it until you reach a certain point. Now let's take it slowly, so we don't get confused. The one who created this concept is the great scientist Fourier. Fourier developed something called Fourier transformation. This man said, now I have a signal in this form. This signal can be transformed from what I call the time domain. The time domain means it is coming in the space of time or at a specific moment. I can transform it into something called the frequency domain. The frequency domain means the signal you see here will take something called frequency. The frequency here is the amplitude, and here is the frequency. So, what does this mean? Aren't you saying you want to get an image of the existing signal? Yes, this signal converts the signal from this form to something called. What you see here represents the strength of the signal and the frequency scales on the x-axis. For example, if I have a frequency of 20 cycles per second, it is represented on the curve as 20. Now, the height of this frequency is related to the magnitude or amplitude of your signal. This is the conversion process from the time domain to the frequency domain. As you can see, this is done through Fourier transformation. Now, the inverse Fourier transformation takes the frequency domain and converts it back to the time domain. If the information comes to you at different times, it can be converted to different frequencies. And if you have the information at different frequencies, it can be converted back to different times. I'm telling you this because we use this in image reconstruction, in magnetic resonance imaging, MRI, through the Fourier transformation. You take all this signal and store it in something called case space. Case space contains all the information of your image, all the frequencies, and then you perform an inverse Fourier transformation to retrieve your image. Right now, I have my original data ready, and I want to take a set of slices. What should I do? I provide the basic B node and set my gradient. I mentioned that I have three gradients, one in the x direction, one in the y direction, and one in the z direction. What does the gradient do? It changes the main magnetic field. Instead of being uniform, it varies. So you have high here, and even higher here. The protons at this point rotate at a different speed than the protons at this point, which rotate at a different speed than the protons at this point. And here it's lower, here it's lower, here it's lower. So this gradient allows each slice to have protons moving differently. It makes it very easy for the machine to determine this location. You tell it you want to take this section, and the machine knows exactly where your table is and where this point is. It knows the magnetic field in this slice, so it sends the RF pulse that I extract from this slice. This is called the slice selection gradient. In this case, I send this slice selection gradient along with the 90-degree pulse that I send, applying the slice selection gradient to it. When you perform any pulse for excitation, you must send the slice selection gradient. Therefore, the slice selection gradient should be on during excitation and during RF pulse transmission. Now, you have performed this excitation and the protons have been excited. After that, you started, as we were discussing about there's just a small point regarding the slice selection gradient that you are applying, which is very important for several reasons. First, it's important to understand that you want to take your slice, whether you are dealing with an image slice or a small image slice. If you are keeping your gradient, you want to take or create a large range of the image. Therefore, you need to work on something called bandwidth. What is bandwidth? Bandwidth refers to the weights of the number of frequencies you will be working with. If you are working on a large image slice like this one, you have multiple locations here, 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 and so on. So your slice is considered large, and there are many frequencies present. Thus, you need to increase your bandwidth. The first point is that this determines whether your slice is large or small. You will find that your bandwidth is large if you are working on a large image slice, and it is small if you are working on a small image slice. That's the first point. The second point is all about the slice selection gradient. The second point is if you are currently changing the location where you want to perform the procedure. For example, I will send my thing to this place, so this is the only place that will do something with it.